Today we get to talk about solids of revolution, and we're going to use a method called the disk method. So that's what this discussion is going to be about. Let's jump right in and get started. Yes, I know, slicing was fun, but now let's consider rotating a curve about an axis, say the x-axis. So you can see here I want to take a look at the curve y equals the square root of x. My interval is from 0 to 4, and you know that curve looks something like this. 0, 0, 1, 1, and then 4, 2. And so it has a curve like that. That's the square root of x. And we are only concerned about the interval from 0 to 4. So I'm just going to dash that in so you know what we're talking about. So what we mean by solids of revolution are the following. We're going to take this curve and rotate it around a particular axis, in this case the x-axis, and it's going to make a solid. This one's going to look something like the end of a bullet. Ooh, I missed it. That thing's supposed to go like that. So as you rotate this curve around the x-axis, it sort of makes this shape like the cone of an airplane or the tip of a bullet. And what we're interested in is what's the volume of that solid that this generates. So this is all filled in. The whole doggone thing is filled in, right? Well, the strategy is this. Every time you rotate something around an axis, your cross-section is a circle. If I just slice this thing, say right here, and open it up, what I would see is a circle. That's why they call this thing the disk method, because we get this little thin disk. Similar to when we were talking about slicing the meat at Arby's. So when you make a circle, you know that the only measurement we're interested in is the radius. And so from our curve here, the picture that we're interested in is when you slice a typical disk, what's the measurement of the radius? Well, just like those other problems we worked on, you can see that the radius is this distance right here from the curve to the x-axis. And anytime you measure from the curve to the x-axis, that is simply a y measurement when you're measuring vertically. So our radius is really just y. And so when we complete this problem, we're basically going to need to integrate the area function, which for us is going to be pi times y squared. So on the next screen I'm going to set up the integral, and then we're going to find out the actual volume of this solid. This is called a solid of revolution. So we have all the information that we need to actually create this integral. I'm just going to stall here while I change the pen. Okay, so we're going to find the volume by setting up an integral that calculates the sum of all those little circles. We're going to integrate over the interval they gave us, which was 0 to 4. Our area function is pi times the radius squared. Now it was pi y squared, but we're going to use what y equals, which is the square root of x. And of course, you know we do dx because there's a little bit of thickness to that disk that we sliced out. And I know how anxious you are to use the calculator to do this integral, but this one is so straightforward. I'm going to go ahead and do it by hand right here. This is the integral from 0 to 4 of pi x, and the antiderivative of pi x is pi x squared over 2. We're integrating that from 0 to 4, and this is a quick little calculation. It's going to be 16 pi over 2, which is 8 pi, minus 0, oops, not equals, let's make that a minus 0 pi, and so this turns out to be 8 pi. 8 pi cubic units. When they don't give us units, we just give the value. The volume of that little shape, remember it looked kind of like this. It's all solid and filled in. The volume of that thing, that cone, that nose cone, is 8 pi. Since I know my drawings aren't spectacular, here's a picture of that solid done with a little bit of perspective and some better colors. And you can see that that slice, that disc that we're pulling out is indicated right here. And the radius, of course, is just the square root of x, which is y. So let's formally define what we've been doing here. This came straight out of your textbook. Solids of revolution, the disk method. The solid generated by rotating a plane region about an axis in its plane is called a solid of revolution. So there's our definition right there. To find the volume of a solid like the one shown, we need only observe that the cross-sectional area, A of x, is the area of a disk of radius r, the distance of the plane's the distance of the planar region's boundary from the axis of revolution. Basically what that means is how far is the curve from the axis of revolution. In our problem it was the y-axis, the x-axis. Okay, I'm tripping over myself as I speak here. The bottom line is, if we're going around a horizontal line, then this is going to be our integral. We're going to integrate from a to b on the x-axis, pi times the radius squared. And what we mean by this is whatever calculation we do to get the radius. In the previous problem, it was simply the square root of x. That function will change depending on the problem you're doing. Okay? But that's going to be our strategy. Find the radius and then square it and integrate. Now, it turns out that not all functions are in terms of x. Not everything is a function of x. Sometimes we have functions of y. And so that definition that we just described was good for functions of x, but let's see if we can expand that to functions of y. So we're going to rotate this curve about the y-axis. This is x equals 2 over y. So a little bit of point plugging here, we can figure this thing out. We're going to start at 1 and end at 4. If I do y equals 1, then x equals 2 over 1, which is 2, so there's a dot right there. And if I do y equals 4, that means x equals 2 over 4, which is a half, which is right there. And so this is a curve that goes something like that. Remember that we're going to focus on the interval on the y-axis from 1 to 4. When you rotate this thing around the y-axis, when you spin it around, it makes kind of a weird little it reminds me of the bell of a French horn or something, but I'll let you decide what it looks like. I'm just going to draw it. So we rotate this thing around the y-axis, and it's going to go something like this. Basically, we reflect it across the y-axis, and we get this solid here, right? It's also reminding me of Devil's Tower right now from Close Encounters of the Third Kind, but I'm sure you don't remember that. Anyway, it's this whole solid in here, everything that's in there, all right? So we rotate it around the y-axis. A typical slice is just a disc, right here. And every disc has a radius. So what we're worried about for that circle is what's the measurement of the radius? And we've talked about how to measure distance in the coordinate plane. When we're measuring vertical distance, we do top minus bottom. When we're measuring horizontal distance, we do right minus left. So basically, to get this measurement, we're going to do the curve minus the y-axis, which is 0. So we really just need this curve. This is our radius. And so that area function for us on this problem is going to be pi times 2 over y squared. You could call that 4 over y squared also. Let's go ahead and set up the integral and figure out the volume of this thing on the next screen. Actually, I fibbed a little bit there. Let's go ahead and look at a better picture first. So here's that shape with a little more perspective and a little bit better drawing. But you can still see that the radius is this curve, or is this little segment here between the curve and the y-axis. And also they're trying to show us the disk right here. And this obviously is a well done image, much better than the sketch I made. But you're going to have to get comfortable drawing your own sketches. These three-dimensional pictures are not easy to depict. And it's going to be important that you can at least get the information you need from the picture, even if it's not going to win any art awards. Now let's get to setting up that integral. Since we're working with functions of y, our volume function is going to be called v of y. We're going to integrate along the y-axis on that interval they gave us from 1 to 4. And then remember, our function was pi times the radius squared. We said that was 2 over y squared. I'm just going to call that 4y over y squared. And then this is dy this time. From here, it's a simple antiderivative calculation. I'm going to factor out a 4 pi. And then the antiderivative of 1 over y squared is negative 1 over y. And we're going to integrate that from 1 to 4 like I mentioned. So when you plug in 4, you get 4 pi times negative 1/4, which is negative pi. And when you plug in a 1, you get 4 pi times negative 1, because it's negative 1 over 1. And so that's negative 4 pi. And when you subtract the negative 4 pi, you get negative pi plus 4 pi, which is 3 pi. And so the volume of that solid is 3 pi cubic units. So in general, we can rewrite that formula for the volume of a solid of revolution when you go around a vertical line, not a horizontal line. V of y would be the integral from a to b along the y-axis of pi times r of y squared dy. And remember, the way we figure out that radius when we're working along the y-axis is right minus left. Make sure you make a note of that to remind you. Working with the y-axis is not easy. I get that. We're not used to it. But it's really no different than working with the x-axis once you get used to it. So after we practice a few of these solids that go around the x-axis or the y-axis, we're going to start moving the axis of revolution around. So here, now let's consider rotating a curve about the horizontal line. Let's say the line y equals negative 1. And we're going to go ahead and draw that line on the page right now. We call this our axis of revolution. And notice I've actually given you the same curve that we had before, and that looks something like this. We're going to rotate this thing around the line y equals negative 1. So again, it's just a matter of reflecting this thing and then sort of sketching in the curve. And actually, the main thing that we're looking for here is that radius. So don't panic if your picture's not perfect. But this is kind of what it's going to look like, right? It's some kind of weird little bowl with the bottom chopped flat. And then remember, we're looking for kind of the volume of everything in here, right? Bottom line is, though, it doesn't matter how good your 3D picture is, because all we're worried about is that cross section. And when you slice this thing with a vertical line, right, when we slice it and open it up, we're going to see a circle. And what's important about a circle is a radius. So that radius goes from the axis of revolution up to the curve. It's this guy right here. That's our radius. And in the plane, the way we measure vertical distance is subtraction. So this top curve here is the square root of x. And this line down here in my mess is y equals negative 1. So it turns out that this radius is the square root of x minus negative 1. So that's square root of x plus 1. So my area function is pi times the radius, which is the square root of x plus 1 squared. Sometimes you'll see that written as 1 plus the square root of x, just so the radical sign doesn't confuse anybody. Okay, there's our area function. Let's integrate this thing. So that volume function is going to be the integral from a to b, for us that's 0 to 4 again, of pi times our radius function, which was square root of x plus 1, and then we have to square that thing, and this is a dx. I'm going to do this one by hand again, simply going to FOIL it out. I can factor out that pi. So I end up here with x plus 2 square root of x plus 1. Little antiderivative action gives me x squared over 2. This one's going to be 4/3 x to the 3/2. And this one's going to be plus x. That's all multiplied by pi, and we're evaluating from 0 to 4. Okay, so here I go. When I plug in 4, I get 16 over 2, which is 8, plus, oh goodness, square root of 4 is 2, 2 cubed is 8, 8 times 4 is 32 over 3, and then there's a 4 there. When I plug in zeros, I get all zeros. So all I have to do is figure out what 8 plus 32 over 3 plus 4 is, and with a little common denominator action there, I come up with 68 pi over 3. And we'll call that good. That's the volume. You can check my arithmetic if you want, but I'm pretty sure it's correct. I did it the first time, made a mistake, then I redid it. Now I'm pretty confident that I have it right. So there you have it. Okay, so let's do one last problem. We're going to rotate a function of y about a vertical line. In this case, it's x equals 5. So let's just kind of draw that in. That's going to be our axis of revolution. We're going to rotate around that. Our function is x equals y squared plus 1. So that's basically a parabola that's just shifted 1. And in this case, it's shifted to the right instead of up because it's a tipped over parabola. So we're shifted here. We're going to be at 1, 1, and then 2, 4, which would be there. So this is the curve we're talking about. Okay. Now remember, we're spinning that thing around the line x equals 5. So this is going to make kind of a weird little football thing, kind of a parabola football. And it's all filled in. Okay. It's like a potato. Now, we're rotating around the axis x equals 5, the vertical line. So when we slice this, we go horizontal. So I'm going to chop this thing any old place horizontally, and what I get is a circle. And remember, what we need on the circle is the radius. So the radius goes from the axis of revolution to the original curve. So that's this guy right here. How do we measure distance in the plane? We do the right, which is 5, minus the left, which is y squared plus 1. That's our curve. So our radius, r of y, is actually 5 minus y squared plus 1, which we can call 4 minus y squared. There's our radius. So our area function, a of y, is pi times 4 minus y squared squared. You have to square the radius. So that's going to be an interesting little integral. Let's check out the fancy picture first, since I have one ready for us. Here's a better rendition of that object. I don't know, I kind of like my picture better. But you can see what we're doing. We rotate around. Oh goodness, this is supposed to be x equals 5. You get the picture. So don't ignore that number there, ignore that number there, and ignore that number there. Fix this right on the fly. And ignore that number there. This is a 4. Oh goodness, I blew this one. Anyway, we're going to do my problem, not the one in the picture. The shape looks the same. Stop laughing. The shape looks the same. You can see the disk that we're slicing, which is perpendicular to that axis of revolution, makes a circle, and you can see here the radius has been indicated exactly the way I did it. Okay, this picture has turned out to be a disaster. Let's go do the math. And so our v of y is going to be the integral along our interval. And I think I mentioned earlier that it was negative square root of 2 to square root of 2. And if I didn't, it was pictured on the graphic. We had 4 minus y squared squared dy. And I was lazy on this one, and I entered it into the calculator. Let me show you what you would enter in, and then we'll just write down the decimal answer. If you're using the calculator on this problem, we're going to do fn int. Remember that fn int function has its own set of parentheses, so I'll use blue to indicate the first parenthesis and the last parentheses when I get done. Now our function also has parentheses. I forgot the pi, didn't I? You're probably yelling at me right now because I didn't put a pi in there. It's pi times the radius squared. Okay, so we're going to have to put pi in here times 4 minus y squared squared, comma, wait, we're not going to use y, are we? We're going to use x on the calculator. Changing the letter doesn't change a thing here. We'll get the same value. Our variable is x, and then we got to do negative square root 2, which will look like that when you type it in, and square root 2. And then you have to close your parentheses. So getting used to using your calculator with this notation for this function is not, it's not easy. You have to be very careful. But if you type it in, it's awesome because you hit the button and it gives you the answer. And if I'm doing everything correctly, I think it's like 101.89. Let's see if I still have the answer on the screen here. Yes, I do. Yep, 101.89. That's cubic units. I'm going to call that good. Double check the math for me on that one and see if you get the same answer. Now, as I close this little spiel here, I'm going to just summarize what we've discussed, and then we'll have you work on some problems. So here's the summary of the disk method that I promised. If you're going around a horizontal line, which means you're rotating this way, this is the formula you're going to use. Pi, notice I just factored the pi out there to make it easier. Pi times the integral from a to b of whatever your radius function is, squared. And since we're rotating around a horizontal line, to get our radius, it's always the top minus the bottom. And that is the distance from the axis of revolution to your curve, however that works out. For a vertical line, when we're spinning around a vertical line, meaning we're rotating around something, like this, the line's going like that. Here's the horizontal line. When we spin around a vertical line, our formula is very similar. It's going to be in terms of y, though. And so our radius function, remember, turns out to be the distance right minus left. That's going to be the distance from your curve, your original curve, to the axis of revolution. Subtract the right minus the left. If you keep this summary in mind, you'll do all right with these problems. But again, you have to be patient. Don't stress out and get frustrated with yourself because your three-dimensional pictures aren't perfect. All the picture needs to do is reveal to you what the radius measurement is. We're just hunting for the function that gives us our radius. Top minus bottom, or right minus left, from the curve to the axis of revolution. And if you keep that in mind and take a deep breath, this will be a piece of cake. This is much more straightforward than figuring out the areas of those squares and triangles and things that we worked with earlier. Because every one of these is a circle, and our whole goal is just to get the radius. This little r, this big R, I guess you could call it, That's our goal. If we can get that guy, we're in great shape. So good luck with this assignment, and I'll see you soon. Take care.